So we're still in chapter 10, hypothesis testing regarding a parameter, but now we're in 10.2, and we're going to work with the specifics of testing with proportions, and we're going to introduce the idea of the p-value, which is very important. It's essentially the most important idea in chapters 10, 11, and 12. So before you begin this, again, you need to understand that we're continuing the idea of hypothesis tests, but we're working with population proportions, and you definitely need to review 8.2 and 9.1 for this to make sense. Explain the logic of hypothesis testing, test hypothesis about a population proportion, and we're going to exclude this third objective. We're not going to do that at all, so you don't have to look at it. Let's look at this flow chart. You should be bored with this by now, but it's important. Chapter 7 introduced the normal distribution, and you need mostly, all right, for the rest of the book and for what we're doing now, you need mostly 7.1 and 7.2. Then chapter 8, the central limit theorem, explained to us what the long-term pattern is for all possible sample proportions, the p-hats, and let us understand that when we're estimating the population proportion p using a sample proportion p-hat, the central limit theorem in 8.2 specifically explained the rules for when this works and how close p-hat should be to p, usually. In 8.1, it looked at the patterns for the x bars, and we'll talk about that when we look at 10.3. But right now, you have to understand that you need to remember everything about the normal distribution, 7.1 and 7.2. You need to understand everything about the distribution of the sample proportions in 8.2. You need to review, not a lot, but a little bit, what we covered in 9.1. And now we're in 10.2, hypothesis test with proportions. Again, we're going to test claims about population proportions p using sample information, specifically sample proportions p-hat. Now, this slide right here just shows what we're doing with StatCrunch throughout chapters 8, 9, and 11. Excuse me, 8, 9, 10, and 11. So in 8.1, we were using the normal calculator. In 8.2, we were using a normal calculator as well. The reason we weren't using the t-distribution in 8.1 is because we had sigma given. The only reason you switch to the t-distribution is when sigma is unknown and you're working with means. Okay, but let's focus on proportions right now. Right now, we're working in 10.2. We're doing hypothesis tests using proportions. And on StatCrunch, what you do is you go to Stat, Proportion Stats, one sample, neither with data or summary, usually with summary. Okay, it's exactly like what you did in 9.1, except now you click the circle. There's a little circle where you click and say that you want to do hypothesis tests and not confidence intervals. So as we already talked, we have 3 objectives, but we're not going to do the third. Okay, it's for small samples whenever NPQ is less than 10. Okay, we'll explain what those subscripts mean in a minute. So we're going to talk more about the logic of hypothesis testing. We're going to introduce the idea of p-values. Again, p-values, that concept is the most important concept in chapters 10, 11, and 12. And then we're going to look at the specifics of testing hypotheses about population proportions. So there are 2 main methods of doing a hypothesis test, something called the p-value method, which is the main method, and something called the classical method, which was used before. Classical making reference to before or older. All right. Both methods work exactly the same, and both methods yield exactly the same results. All right. And we have to look at the classical method a little bit, but our main focus is going to be the p-value method. And in the p-value method, you compare the p-value that's calculated on StatCrunch to a given level of significance, alpha. Alpha is going to be the size of the reject zone. The classical method works the same way, but it compares a test statistic to a critical value. See this alpha right here? Alpha will determine what the critical value is. All right, and the test statistic also comes from the sample in the same way the p-value does. And so they're 2 different methods, but on some conceptual level, they're the same idea. So Assume that previously we determined that 50% of the public was in favor of banning cell phones while driving. That's going to be our null hypothesis, H naught, P equals 50%. Okay. And let the alternative hypothesis that more than 50% of the people favor the policy. So that would be our alternative hypothesis would be that P is greater than 0.5. All right. A researcher obtains a random sample of 1,000 people and finds that 534 are in favor of banning cell phone use while driving. So we get a P hat of 534 divided by 1,000, which is 0.534. Okay. Does this sample information suggest that we should believe that the population proportion has increased? All right. In other words, would it be unusual to obtain a sample proportion of 53.4% or higher from a population whose proportion is 50%? What would be convincing evidence to cause us to believe that the new proportion is higher? Slide. This is a very important phrase. It'll be on the test. All right. The phrase statistically significant, whether you see it in a textbook or in my lecture or in my videos or even in like sort of the newspaper or magazines or on TV, statistically significant means only one thing, and it means there was sufficient evidence to reject the null hypothesis. Okay. A p-value, and we're going to introduce that in detail in a moment, is what's used to determine if your observed results are unusual or usual. Okay. What's going to happen is we're going to set up a diagram, we're going to set up a distribution based on the assumption that the null hypothesis is true, and if we get some weird sample results back, we're going to reject the null hypothesis because our results were unusual, okay, and we don't think that the population proportion is what it was previously. So look at this right here. This is a nice diagram. Suppose we assume, look over here on the left, that the population proportion is 50%, 0.5. We set up this distribution, notice it's a normal distribution, and we assume that the population proportion is 50%, so that goes in the middle. I'm going to slow down here a little bit. I need you to remember that the mean of the distribution of all possible p hats, mu of the p hats, equals p. Assume that the mean, just assume, we don't know for certain, we assume the mean's 50%. Then we take a sample and we get a p hat being 53.4%. We mark it on the x-axis right here. So we want to know what would be the probability, of getting a sample proportion this high, or more so. That's why we keep going out to the right. This high or more so if this were really true. The p-value is this area right here. It tells us what's the probability of getting a sample statistic, this p hat, this extreme or more so, if we truly believe that p equals 50%. The computation of the p-value will be done using StatCrunch, but the most important part will be the conceptual understanding of the p-value. You absolutely have to do some extra research on this. You need to read the textbook about p-values. You need to Google p-value. You need to go to the YouTube and look at some videos about the p-value. It's the most important concept in chapters 10, 11, and 12, and you won't understand anything about hypothesis testing until you understand what a p-value is. So whatever you do, do additional research about p-values. Again, go to Wikipedia, Google it, look at some YouTube videos, read the textbook, but you have to spend some time on this. It's the central idea for chapters 10, 11, and 12. So formally, a p-value is the probability of obtaining a sample proportion equal to or more extreme than the one found in the sample if the null hypothesis is true. So the most important thing you can remember about the p-value, it's based on the assumption that the null hypothesis is true. Getting back to our previous example, we were assuming that the population proportion is 50%. All the conditions are met, so the distribution of the p hats has a normal distribution. Again, please review 8.2. So in this particular case, we're assuming that this diagram has some reality, and we're also assuming that the center of this diagram is 50%. Then we take a sample, and that sample statistic, the p hat, was 0.534. We come over here, we mark 0.534. It's a right-tailed test because we want to check to see if the proportion has increased, meaning right-tailed. We mark that there, we shade this region in, and that area in the blue region, light green or whatever, is the probability that p hat is greater than 534, which is the probability of obtaining a sample proportion, this p hat, equal to or more extreme than the one found in the sample if the null hypothesis is true. We'll talk about that more and more, but let me just show you something that you may think is a discrepancy. Do you see here where p hat's greater or equal, and over here p hat's just greater? It's the same. For any continuous distribution, you should have seen that by now in chapters 7 and 8 and 9, that for continuous distribution, it doesn't matter what you put there, whether you have just greater than, like on the right, or greater than or equal, it's the same, but the greater than or equal to matches this equal to or more. To compute p-values, you just go to stat, proportion stat, sample, either data or summary. If they give you the number of successes and the sample size, then it's summary. If you have to compute like just raw data, it'll be data, and then you'll get a p-value from that. Hypothesis testing using the p-value approach. If the probability of getting a sample proportion as extreme or more extreme than the one obtained is small, under the assumption that the null hypothesis is true, reject the null hypothesis. So let me explain to you. We come back here, and all this is on an intuitive level is we make the assumption based on the null hypothesis that the mean is some specific number, in this case 50%. If we take a sample test statistic and that number is close to the middle, then we're going to assume that the null hypothesis is true. Now that's a little bit erroneous the way I phrased that. I'm just trying to make it clear to you on an intuitive level. But if the test statistic, in this case p hat, is close to the center, right, close to the center, then we're going to fail to reject the null hypothesis. Notice here, if the test statistic, this p hat, fell close to the center, then the shaded region from the test statistic to the right would be a huge area. So the p-value gets smaller because the p-value is this shaded region. The p-value gets smaller the further you are away from the center. If your test statistic is close to the number that you thought was true, meaning back here towards the middle, you're going to fail to reject the null hypothesis. And on a right-tailed test, if you're very far to the right, meaning your test statistic is way out here, then you're going to say this is very unusual, and you're going to doubt that the null hypothesis is true. You're going to say we reject the null hypothesis. But you need a formal and technical way of making that decision, and that's where the p-value is compared to alpha. Alpha is going to be the size of the reject zone. If the p-value is larger than alpha, you're going to fail to reject the null hypothesis. If the p-value is way out here and smaller than alpha, then you're going to reject the null hypothesis. Fail to reject if you're close to the middle and a large p-value. Reject if you're way out here and you have a small p-value. So when the p-value is greater than alpha, you fail to reject. That means you're close to the center with your test statistic. If the p-value is small, less than or equal to alpha, then you reject the null hypothesis because that means you have an extreme value. This is a screenshot, so these are not live links. What you should do is go to YouTube and just type in p-value and find some very basic, you don't want anything advanced, right? Find some very basic videos and watch them. Again, you have to understand what a p-value is. You're going to have a claim about a population proportion, and you're going to use that claim to set up the null and alternative hypotheses, right? This 1 and 2 here, check the conditions and set up the null hypotheses, they're simultaneous. In fact, to set up the null and alternative hypotheses should probably come first, because the conditions are going to be based on the null hypothesis. The conditions are going to be based on the null hypothesis. When you set up your level of significance, it's based on the consequences of both type 1 and type 2 errors. But in a textbook situation, classroom situation, your level of significance alpha will always be given. Always draw a diagram, left-tailed, right-tailed, two-tailed, based on the alternative hypothesis. All right. Compute the p-value using technology and make a decision and state your conclusion in the context of the problem. Prior to stating your conclusion in the context of the problem, what you do is you make a formal decision. If your p-value is greater than your level of significance, you fail to reject. If your p-value is less than or equal to your level of significance, then you do reject. If you're taking this class and you're going to take a test in the classroom, right? Not all of you will, but some of you will, then this is an example problem that I would ask. I would type in a paragraph from the homework that I would ask you, which distribution are we working with? Are we working with x bars? Are we working with p hats, right? Are we working with means or proportions? I'd ask you to demonstrate that the necessary conditions are satisfied. I would ask you to set up the null and alternative hypotheses, all right? I would ask you to draw a diagram labeling the mean and shading in your p-value region, all right? I would give you the p-value because you won't have the computer to use StatCrunch, and then you'll have to state your conclusion. The conclusion's based on a comparison of the given alpha. Up here it's 5%, but that could change in comparison to the p-value. So the conditions for this are pretty simple. You have to have a good sample, but that's always true no matter what, all right? But you have to have n p subscript 0, q subscript 0 greater or equal to 10. What does this mean? Well, q subscript 0 is 1 minus p subscript 0 like before, all right? This is just the probability of 1 minus the p. But these numbers are corresponding to the null hypothesis. Listen to this carefully. The number that you use here is the same number that you used in the null hypothesis. We'll look at that later. And then always when you sample without replacement, you have to make sure that the sample size is smaller than 5% of the population size. There's 3 ways to set up the null and alternative hypotheses. Okay, pretty easy. Difference, decrease, increase. You select a level of significance based on the seriousness of making a type 1 error. That's what this book keeps saying, but the truth, and that's why I have it here, just to be consistent with the textbook, but the truth of the matter is you have to look both at the consequence of a type 1 error and the consequences of a type 2 error. Remember that type 1 is false positive, type 2 is false negative, and you adjust the sensitivity of the test based on alpha depending on the consequences of making type 1 and type 2 errors. You should check out this link. Now, these links are not live because this is a video, but if you go back to the PowerPoint slideshow, you could just click on this link and it would open up. However, well, actually, let me open it up right now. This is really nice. This is like a statistics tutorial site, and it talks about setting alpha and all this here. All right, two-tailed, reject region, and alpha levels. It's fairly interesting. Okay, let me go back. But you'll need to go back to the PowerPoint, the actual PowerPoint, to be able to open this up. It won't open up off the video, or you could just copy down this right here. This is the address. So we're going to have to briefly, talk about the classical method, and we'll do that in a minute. But when you have the classical method, you have something called a test statistic, subscripted z subscript 0. And you also have something called a critical value, z subscript alpha, z sub alpha, or z sub alpha over 2. If it's two-tailed, you get half of alpha on each side. Now, we'll talk more about the test statistic later and the classical method. Okay, but whenever you do StatCrunch, you're going to see the p-value in this box right here that I'm looking at in the bottom right-hand corner of the screen. And the number next to it is going to be your test statistic, this z subscript 0. This is required in the homework occasionally. All right. They're going to say, what's the test statistic? It's denoted by z subscript 0, and it's always this z stat number right next to the p-value. That will be important for your homework. If you have a left-tailed test, right, left-tailed, right-tailed test, etc. How do you do this using technology on StatCrunch? You go to stats, proportion stats. This is exactly the way you did this before in chapter 9, and you choose summary, right? You tell it the number of successes, the number of observations, and now instead of doing confidence intervals, you do a hypothesis test, you hit compute, and you get the test statistic here and the p-value right there. One of the things that you have to understand is that you never accept the null hypothesis. You never prove that the null hypothesis is true. You never say that we've just concluded that the null hypothesis is true. It doesn't work that way. Every time that you write a conclusion, and these conclusions are very technical and formal and don't allow improvisation, you always either say there was sufficient evidence to conclude that the alternative hypothesis was true, or there was insufficient evidence to reject the null hypothesis. If the p-value is greater than alpha, you fail to reject the null hypothesis, and you say you cannot conclude that the alternative hypothesis is true. If the p-value is less than or equal to alpha, then you reject the null hypothesis, and you say there was sufficient evidence to conclude that the alternative hypothesis is true. See the handout. So now we're going to do an example. And so in 1997, the population proportion was 46% for people who didn't trust the media. And in 2016, they did a poll of 1,010 adults, and 525 stated they didn't trust the media. At the alpha equals 5% level of significance, is there evidence to support the claim that the percentage of Americans that don't trust the media, blah, 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 accurate, blah, has increased? Okay, so here's what we got going on. We want to know if p is greater than 0.46, the previous amount. We want to know, has it increased? First, you have to verify the requirements to perform the hypothesis test. Do you see where this is coming from? Let me go over here. Do you see right here, this is the null hypothesis, p equals 0.46. Do you see how the null hypothesis is subscripted with a 0? Well, when you check the conditions, you check n p subscript 0 times 1 minus p subscript 0. But this number, the p subscript 0, is super important, is coming from the null hypothesis, and that's why that's 0.46. When we do this, we get 250.8, which is obviously greater than 10, so this is the main condition that's been met. Obviously, we need a good sample, and as always, when we don't have replacement, we need the sample size to be small, but we have that met. So I'm going to briefly talk about how this is done using the classical method. You still have the same conditions, you still have the same idea where you set up the null and alternative hypothesis. All right, you still have a level of significance here. This alpha right here is the size of the reject zone. The level of significance is always the size of the reject zone. And now we get a sample proportion of 5251010. We take this number right here, notice we put it in this formula, and what we're computing is a z-score. We want to know how many standard deviations above the mean this 52% is. It came out to be 3.83 standard deviations. That's our test statistic. Okay. Now we're doing a right-tailed test. The reject region is alpha. That's the reject region. That's what alpha is. The level of significance is the size of the reject zone. Okay. So we have to figure out what a critical value is. One of the main things to remember about the classical method, it converts everything into standard normal. That's why they're using z's. Classical method, everything gets converted into standard normal. So right here, we're looking at a standard normal distribution. Okay, standard normal. And they tell us that this green area, the alpha region, is 5%. So that means that this number right here, z sub alpha, is 1.645. 0 will be in the center. Remember, standard normal. And if we move out here, 1.645 standard deviations, that'll be the threshold for causing us to reject the null hypothesis. Okay, so the test statistic is 3.83, so the test statistic is way beyond, right? Way beyond the critical value. The critical value marks the beginning of the reject zone, all right? It's based on the value of alpha. It changes with alpha. But in this particular case, the threshold where we say this is okay and this is reject, okay, reject, okay, reject, is at 1.645, again, based on alpha. We compute the test statistic from that p-hat that we compute by converting it into a z-score. That means it's 3.83 standard deviations out here to the right. It's way beyond the threshold, so this result is very unusual, and so we reject the null hypothesis. I've tried to eliminate most of the classical approach from the homework, but it's always going to appear in the homework somewhat because they like to compare and contrast the two versions in some of the homework problems. So now we're back to the p-value method. Let me quickly review what we've done. In both cases, you check the conditions. In both cases, you have a null and alternative hypothesis, all right? But now, instead of doing a test statistic and a critical value, we're going to use a p-value approach. So we check the conditions, we set up the null and alternative hypotheses, right? The level of significance in the field, if you're a researcher, you'll have to decide what level of significance you want. The rule of thumb is 5%, sometimes it's 10%, sometimes it's 1%, but in a textbook or classroom setting, it's always going to be given. Okay. You draw your diagrams, right tail, two-tailed, left tail. Notice here alpha over 2, because alpha is the size of the reject zone. It always adds up to alpha. If there's only one piece, it is alpha. One piece is alpha. If there's two pieces, each side's alpha over 2. All right. And so we compute the p-value, and the p-value is determined by how far away from the center, the test statistic, the p-hat, lies. So in this particular case, our test statistic was 52. Oh no, it wasn't. Our test statistic was 51.98%, or 0.5198 rounded to 4 decimal places. See, 0.5198. The center of our distribution, this is a right-tailed test, the center of our distribution was based on the null hypothesis, so it's at 0.46. So we want to know, is this value 0.5198 from the sample, is it close to what we thought would be true at 46%, or is it too far to the right? Well, our p-value being super small means that we're way to the right. In fact, we're 3.8 standard deviations to the right. Anytime your p-value is smaller than alpha, that means you're way to the right, and that means reject the null hypothesis. So since the p-value is less than the level of significance, we reject the null hypothesis. We say there is sufficient evidence that the alpha equals 0.05 level of significance to conclude that the percentage of Americans that don't trust the media to report fully and accurately has increased since 1997. Okay, what you have to understand is your conclusions are always in terms of the alternative hypothesis, all right? Has increased. If we didn't reject, we would say we cannot conclude, all right? But the conclusion is always in terms of the alternative hypothesis. This right here is just showing you that if they're talking about majorities and less than half, more than half, then your null hypothesis is always equals a half. If they're talking about majorities, or it's talking about less than half or more than half, then your null hypothesis will be equals 0.5. And then less than a half, less than, greater than a half, right? Majority, greater than. Just to remind you, we're not going to use the classical approach. If you do the classical approach, that's why you have to convert everything into z-scores. That's what they're doing here. Okay. We're not going to do anything by hand, so we're going to do the p-value approach using technology. So we're not going to look at the classical approach unless we have to in the homework, all right? You don't need to look at it at all in the textbook. We're going to do a p-value approach, but we're never going to do this by hand, ever. Okay. We're always going to use technology. We're always going to use the p-value approach as our first method, all right? And we're going to use StatCrunch. Do you see where they're using the word majority? Whenever they're using the word majority, you're going to have a null and alternative hypothesis that look like this. The null is going to be 50%, and then the alternative is more than 50% based on the idea of what majority means. I would actually do this using the p-value method, but you're going to have to understand the connection between the classical method and the p-value method in order to get the right choice in the homework. So they don't actually ask you to set this up as a hypothesis test, but you should, okay, in order to understand what to do on StatCrunch. And so the null hypothesis is that the population proportion is 1.8%. The alternative hypothesis, that is more, so we have greater than, 0.018. We do one sample proportion summary, and we get a small p-value, meaning it's smaller than the given alpha. It's at 5.9%, and alpha is set at 10%. So we know we're going to reject the null hypothesis, and we have sufficient evidence to conclude that the rate is greater than the 1.8%. Okay. there's sufficient evidence to conclude, all right, that more than 1.8 experience flu-like symptoms. But let's talk about why the test statistic is obviously greater than the critical value. Whenever you have a right-tailed test and you're going to reject the null hypothesis, that means your test statistic was further to the right than your critical value. Whenever you have a right-tailed test and you're going to reject the null hypothesis, that means your test statistic, your p-hat, ended up further to the right than the critical value. That's how I would do it.